Thank you all for joining us for today's Kenworth Northeast Training Academy. We really appreciate you taking the time to hop on the call with our friends from Meritor to take a deeper dive into failure analysis of common truck parts. My name is Melinda. I'm the Director of Marketing here at Kenworth Northeast, but more importantly, we're joined by Peter Adair and Jason Bauman from Meritor, and they'll be leading today's session. So cameras and audio are defaulted to off to reduce our background noise and distractions during the sessions. So if you have any questions, go ahead and pop them in the Q&A anytime, and we'll address them throughout the call. In addition to today's training, we've also got a really great lineup going on through actually October of this year that'll include both virtual and in-person events. One that's actually not listed on this slide right here is in May. We have a whole series of AC trainings that are happening on site in our locations. And if any of them are near you, you can go ahead to kenworthne.com/events to register for those. And you'll also find the rest of those sessions that are going to be planned through the year as well. All right, with that, we will go ahead and turn it over to Peter.
Good afternoon, all. We're just going to switch over here our camera really quick. There we go. Everyone should be able to see me. Everyone should know their Zoom settings. So for those of you that are not familiar, my name's Jason Bauman. What's up? Hold on. Can you stop sharing, Melinda, can you stop sharing?
Sorry.
There we go.
Okay,
all right, now I should be full screen. Okay. I don't really like seeing myself this big personally, but I'm on an 80-inch monitor on this other side. So, all right. So my name is Jason Bauman. Good afternoon. Thank you for coming to our second session with you guys today. Our first session was with electrification. So welcome to the second session. We're going to be covering failure analysis with this session. I've been a trainer with Meritor, now Cummins Meritor. If you weren't familiar, we were bought by Cummins in 2022. We're going on our second year here in August as being part of the Cummins umbrella. So we are now Cummins Meritor. So if you weren't familiar with that, you are now, and welcome to the Cummins Meritor brand. Like I said, I've been a trainer with Cummins Meritor for 14. This year will be my 14th year here. Started out in the on-track warranty call center before that, wrenched before that in shops, and did engine machining, and then also did residential construction to pay for college. So been around the block, pretty much can fix or repair anything. So that being said, we're going to dive right into it. We're not really, because it's a shorter session for this class, we're going to dive right into kind of the failure analysis portion of it. So you're going to go from me to we're going to go right to the camera so you can see the broken parts. We'll do our best to show you what's going on and what caused those failure modes. So let's just dive right into it and go to our first failure example. This is a really quick.
Jason, really quick, the screen has gone black. Oh, there it is. It just came back. You're good.
Everything good?
Yep, okay. It went black for a few minutes, but it just came back.
Okay, so it's all right. There's a thing on our end that's causing it. It's not your end. We can fix it, but it might black some things out. So we're going to let it ride for now. With this being said, last thing before we jump into it is this is open forum. There are only 11 total in the room. So don't be afraid to unmute. Don't be afraid to ask questions in chat. If you want to see it at a different angle, if you want to understand more of what caused the failure mode, I'm going to do my best to kind of put it all in there and throw it all out there for you. So don't be shy is all I'm saying. So first example we're going to talk about is lubrication failure examples. So what lubrication failure modes do we see, and how does that lube affect the life of the components or what we're looking at, and what failure modes is that going to institute? So we're going to jump over to cam 2. I can't see anything, but I hope you guys can. Looks good on our end now. So if we look at this gear, it looks like a normal ring gear section. I don't see anything fundamentally sticking out. Again, we're going with lubrication failures. So if I look at the drive side of this gear, we can see that it's heavily scuffed and scored. And the coast side not nearly as bad as the drive side. Remember, our drive side is going to have majority of the torque and stress on it, which is why we're going to see more excessive wear on the curved side of the tooth. But you guys can see this striations through the tooth. This is not part of our machine process. This is not part of our lapping. This is metal to metal contact. So when we're looking at an example like this, axle oil is supposed to have a certain additive package. The main additive package we are looking for as Cummins Meritor is GL5 or an EP additive. If you lack the GL5 or the EP additive, you're going to get what we call crow's footing, which is what this is. Now, this could also be caused by wrong lubricant. So if I have the wrong oil installed in the axle, and I can tell you, if you can dream it, it's been put in there. Engine coolant, brake fluid, transmission fluid, straight weight gearbox oil. The best one is mineral oil, mineral spirits. So if you can dream it, it's been put in our axle and it's been filled. So this could be either the lack of GL5 or you could have really old lubricant. And with really old lubricant, you're gonna eventually wear out the additive package or the GL5, which is going to cause the lube to still cool. The lube to still cool and keep and prevent the burning and overheating. But what we're going to get with older lubricant is the additive package is going to deplete over time. So the other thing that's going to determine your oil change interval besides age of lubricant is going to be your route, your terrain, and your region. So if you're operating in more desert climates, you're probably going to want to do more lube samples to see how much dust and dirt you're getting into your oil, which could also cause an abrasion into the oil. So if you're changing oil or you're pulling a seal and you're seeing that the bearing looks kind of like foggy or cloudy, that is a sign you have an abrasive in your oil. And that's going to mean that you're going to have to start doing your lube change intervals a little more often. So crow's footing is the first failure mode with lubrication samples. So that is going to be a lack of GL5, wrong or depleted lubricant, or just super old, just obviously depleted. Again, if you're going to overheat too, we have a temperature rating we're looking at. We want to keep it around 250 degrees or lower. Every 10 degrees we go over that 250 degrees, we deplete the additive package by 10, 20, 30, 40%. When we get to the 300 degree mark, we're literally burning the additive package out. So if you've seen oil temps that spike towards that 300 mark, again, a lube sample is going to be your best option for determining if you have any lube life left. Typical lube life for us for a line haul over the road for, let's say, your Walmart or Penske or Ryder truck is around 500,000 miles with zero off-road pure turnpike. So the minute you start off-roading or you start doing high mountains or steep grades, you're going to end up with a different lube change interval. So again, this example was crow's footing, wrong depleted or wrong lubricant, basically, essentially on that one. So what happens with the low lubricant? So the one major thing we're going to get with low lubricant is we're still going to get the crow's footing, which I'm going to show you, but we're going to get an additive on top of that. So let's go to camera 2. So we can see on this example, I have the crow's footing. I have the really deep grooving and scuffing into the gear teeth. And this one's going to be a lot deeper and way more prevalent. And main reason is this was low and depleted. So you can kind of see there's some bluing down deep into the gear root tooth, showing signs of excessive high heat. So the main thing you're going to get with a low lubricant that you don't get with proper level is you're going to get carbon coking. So you're going to get burnt oil all between your gears and your teeth, right? So all the burnt oil that shows up on the non-working surfaces. And that's what you're basically looking for in a low lubricant versus wrong lubricant. So when we look at the two pieces kind of side by side, we look at this one has, oh, sorry. This one has no carbon coking down on the inside, where this one's full of burnt oil and lube and has bluing. So again, wrong and low. So carbon coking is going to be a huge thing to look for. If you have burnt oil, you already know that you are in the position of low lubricant. Now, when we look at this guy, this is going to be wrong or depleted lubricant. And the main thing I want you to notice as a technician, when we compare it to another gear, is when we look at the top lands of the gear, see? Oh, get that burn oil off there. When we look at our top lands here, I have top lands. Even though this is badly damaged from low lubricant, I still have them. You can see here they've razored out. So this thing ran a long time. Now, if I didn't have cooling capacity, I wouldn't have gotten to this point. So meaning if I had low lube, I'd look like this, where I'd still have some top lands left. But because I was full, but had the wrong oil in there, I was able to wear the top lands completely down to a razor sharp and wear through the hardened case steel that we have on the gear, leaving a nice matte finish instead of a polished machine finish. I'm getting a matte finish. I'm still getting some crow's footing, but not enough to where it's deep enough because we're into that soft steel on these teeth. So no more hardened shell. So we don't get that super deep grooving and crow's footing on the gear teeth that we see on the low lube. All right, so that is wrong, depleted, or low lubricant. Cam one. So that's wrong, depleted, or low lubricant. Remember, with low, you're going to get the burnt oil and you're going to get the smell. Every technician knows that smell. It's not magical by any means. Once you've smelt it, it never leaves your nose. So the next lubrication issue is going to be what we call spin out, right? Every technician who's been in the field long enough has seen spin out or friction welding. Now, key thing is understanding where that friction welding is going to take place, because they're essentially, we're going to cover a couple different positions here, but you essentially have your main diff, cross and pinions, right? And then you have, so we'll just throw it out there. You got your main diff, cross and pinions, right? And then you have your power divider, cross and pinions. Remember, the main difference between a power divider cross and a main diff cross is the spline section. So when we look at spin out potential, what is spin out? Spin out is excessive differentiation, meaning you have the front axle being held with the rear axle spinning, or you have the front axle spinning with the rear axle being held. Either way, you're having a excessive differentiation or a loss of traction. So you have a difference in speed from front to back, or you have a difference in speed from to left to right, or both combined together, front to back and left to right. So there are a couple different places we can have spin out. The main place that we talk about is going to be cross the pinions. That's the easiest one to do as a driver. If you're seeing a lot of spin out with your fleets or with certain drivers, teach them how to use their locks properly. That is the best way to avoid the damage we're going to look at now. So when we look at spin out, we're looking at this cross here, right? I have this guy here. So I have what I would call a single leg spin out. So you can see the metal to metal, the friction welding or the gulling, right? These guys are still attached. They still spin. But the key thing with any spin out or excessive differentiation is, do they come off? And the answer is no. On a normal built carrier, these pinions would come off of the cross. And as you can see, this one is fully seized and will not spin, and which is why we broke at the cross hub. So there are different ways to look at it. You can see with these gears pulled off that the metal on the inside, what we're seeing here in here, is what's left of this cross leg in a different scenario, right? But everybody friction welds. Everybody has spin out. Now you can reduce spin out and how much damage you're taking by understanding how to use your locks. So it's a matter of driver training. When you see this type of damage, it's literally the only thing you can do to mitigate it is train your driver. So the pinions to cross are going to be our main spin out scenario. We can see this is a power divider or an inner axle differential, or IAD. And I have 3 locations in the IAD I can spin out. I can spin out the cross and pinions. I can spin out the side gear to input shaft. So a side gear typically will have a hole in it. So we'll move this guy. So this is a normal side gear, right? Hole. I can see my output shaft splines. I can see all the way through, right? Just a hole. And then this is what happens when we weld the input shaft to the rear side gear. And you can look on the back side and you can see the input shaft, or what's left of the input shaft, hanging out there. I really like this light setup that we did on this one. It's working out much better. Sorry, we're just doing a new lighting setup we're trying. So you guys can see, and ladies, where that spin out's occurring and how that input shaft gets stuck in there. This is one of the locations we lube when we have a pump model. This is to prevent this damage from occurring. The third and final location of an interaxle differential spin out is going to be the helical gear to input shaft. So we can see down inside here, I got metal to metal transfer. I do not have the shaft that goes with this, but I can show you guys a different one. But metal to metal transfer on 2 sides of the gear. So this gear was pretty much welded to the input shaft and was pressed off after the diagnostics was performed. So a couple different locations to have spin out. Now, those are considered pretty light in terms of spin out until you look at something this, right? This is a 14X IAD. As far as I can zoom out. And what we've done here, what the driver's done is they've gotten this so hot, they've melted the bowl into a diamond. They've detempered or rolled back the heat treat on the pinions and cross and turned them into softened seal. This thing's so badly mushed, the gear in the back is literally stuck in the bowl because of the shape of the bowl at this point. So this is a really bad spin out, but showing the quality of our build, our bearings stayed together. Regardless of how much heat was put out here, our bearings maintained and held this system together. So the input shaft also survived this damage, and you could actually reuse the input shaft on this one. So like I said, spin out is our #1 failure point. And it comes down to drivers knowing how to use their stuff. So in this instance, we have the input shaft welded to the rear side gear. This system got so hot, we literally melted and rolled steel. And then it got hot enough to where it detempered the heat treat on the output shaft and the output shaft snapped off. That is not the input shaft. That is right here, down stuck inside. And you can see the spline section of the IAD. And then back here is the output shaft, or what's left of the output shaft. So multiple areas in which we can spin out or damage. So I always like to pose a question, because who doesn't like a little interaction? Would you guys think this main diff cross is part of a tandem or a single? We can try to get the chat moving here. We'll try it. So based on the wear characteristics we're seeing, right? Really excessive wear. Let's look at a different cross spine over the top. So our cross legs are supposed to be nice and flat, show a little bit of wear, not much, versus this one where metal's pooled and cooled and repooled in multiple locations. We got more metal pooled down here. This is an extreme spin out scenario, or extreme scenario of someone of driver abuse. My guess is it's a rear single or a part of a tandem, because we'd be able to use the IAD lock to get us home after we lost drive due to all this movement of the internal gearing of the main differential. So most likely part of a tandem for me. All right. So do we have any questions on the lubrication failures that we just saw?
And just
All
so
right.
everyone knows, I did make it so that you can unmute yourselves if you want to jump in with a question or to respond to something.
Yeah, don't forget, we have the chat function too. We're monitoring chat on the backside so we can see everything you guys are typing or want to type. So don't be afraid. I don't bite, I promise. So, all right, now we're going to get into what we call instantaneous fractures or instantaneous overloads. So first one we're going to look at is the most common, and it's called shock load. Shock load is going to be our most common failure mode. And in terms of what does it look like, how do we identify it? And we can see here, we got a piece of ring gear that's broken on an angle here, right? Put it at the angle you guys would see it at. So this is the angle that the gear broke, right? So it was on drive side, it was on that convex side. So gear broke off in this direction. So the main thing that identifies shock load or instantaneous failure, meaning you've hit the max strength of the part, there is no more for it to give, is going to be this right here. So if we zoom in on that, focus. So we can see zoomed in on here, this is a rough and crystalline break. So if I angled this the right direction, you'd see some crystals in there or some sparkles. That's really what we're looking for, is some sparkles. But you can see these other teeth broke similarly. I got rough patch here, and then on this back tooth back here, I got a rough patch down here. Now what you're seeing here, these lines and striations here that aren't rough and crystalline, this is the pinion rolling back over this gear a few times and smoothing these rough striations out. Has nothing to do with the original break. It just has something to do with the way the truck was being driven and how it was rolling through the break. So anything rough and crystalline like this break, that's instant. There is nothing else you can call it. That means for this one, we deemed it was essentially, because of the way it broke, we're trying to always keep three teeth in contact with the ring gear at all times. So you're gonna have a heel, a full tooth, and then your toe. So we're always trying to keep one full tooth in contact with the other two coming on and going off of the pinion while we're rotating. So you can see this was a three tooth hit. Most likely was a clutch dump. Guy's foot slipped off the clutch at a higher RPM and he just popped the clutch, or he was stuck and he popped the clutch. Either way, it was some type of instant hit to the gear set, and that's exactly how our pinion comes in contact. So that's exactly how we broke it. So rough and crystalline is how we would define a instantaneous overload or shock load. All right. Which one's next, Pete? Is it the shafts? I think it's the shafts. Yep, shafts. All right. Time for some fun examples. So we're going to look at some more shock loads, but more on the axle shaft side. So when we're looking at passenger car, I know we're not in that business. Much smaller, much lighter parts. When we're looking at passenger car, in passenger car, they put in what we call a drivetrain fuse or a powertrain fuse. And that's going to be your CB shaft or your U-joint. They design them to fracture and break at a certain point, so we don't break our transmissions and we don't break a bunch of other stuff. Now, coming into commercial truck, we don't have a fuse in the drivetrain or powertrain. So it will always, always, always find its own weak point. In the last instance, it was the ring gear. Before that, it was lubrication-based failures, which are not a weak point, but more of a lack of maintenance. So everything moving forward now is going to be the truck finding its own weak point and us determining what exactly that weak point is going to be and why did it happen. We make parts. We don't make bad parts. I mean, we're making about 2,000 axles a day, so we really don't make bad parts, but people find the weak points of our parts all the time. So in terms of axle shafts, let's pose a question to chat. How far can you rotate an axle shaft before you snap it? What's your guess? Let's have some fun. Let's throw some numbers out there. Is it 60 degrees, 80 degrees, 90 degrees, 720 degrees? What do you think it is? All right.
50 to 75.
50 to 75 degrees. That's a great guess. Thank you. All right. So when we're looking at axle shafts, depending on the series, doesn't matter. It's going to depend on the series because each series has a different diameter shaft. We can go anywhere from 280 degrees all the way up to like 420 degrees. Most of them will do 360 degrees. So, which is crazy when you think about, you know, a 1.5 inch, 2-inch diameter shaft twisting all the way around before it finally snapped off. So I'm going to teach you guys how to identify that here right now and determine, was it a bad part or was it the driver stuck? So let's look at our first example. Really hard to tell what that is. All right, so let's spin around here. So we can see we have a axle shaft chunk. I got my flange, my shaft, and where I broke off. And you can kind of see where it broke. Now, the cool thing about this is called a torsional tensile fracture. Tensile because it's at a 45-degree angle. Now, we have a shear fracture, torsional shear fracture, which we'll look at next. But in this instance, torsional tensile. So tensile is always going to be your 45-degree break. Now, what does the 45-degree break tell you? It tells you it was loaded, meaning it was already twisted and kept twisting as it snapped. So it's very similar to when you're watching drag racing, when they line up at the light and they load all the powertrain up, right? They get up to the light, they hold the brake, and they load everything downstream. Transmission, drive shafts, axles, gearing, everything gets loaded to whatever 3,000 RPM, and then they let go of the brake. That's exactly what this stuff's doing when it's in the truck. It's going to twist, 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 and then it hits a point where that twist releases that energy, and that's what gets the truck up and moving. In this instance, we twisted it beyond what it was capable of, meaning either we had too much load on the truck, we were stuck in the mud, we were stuck on ice, and we hit dry pavement. Either way, we were already twisted or loaded when this break happened. It's the only way to do it. So when we look at it, it's a 45-degree angle. The other thing we're going to look at is these guys here. Right? All these striations that are into the steel, these what we call mountain peaks. You guys can see them sticking up there. So these mountain peaks that we call them, they're called chevrons. Chevrons and mountain peaks will always point back to the original start of the break. So if I look at where my chevrons go and I look at where my grain structure goes back to, everything points to this location right here. This is called a ratchet mark or an origin. This is exactly where our brake started. This is exactly was the reason this happened. So if I were to analyze this, this happened while the vehicle was loaded, it was moving, but what caused this shaft to break? The main thing that happens with technicians and mostly all of us is that we concentrate on this section right here. We're going to look at this brake and go, oh, that was a bad part. Well, this is not a bad part. This is a very good part. It was just broken. So I could blame heat treat, and I could go, well, the heat treat was the problem. Well, if I look at this part here, I can see that it was heat treated. So I have a very coarse grain structure in the middle with a very fine grain structure on the outer edge. This fine grain structure, I'll show you my other example, which really shows that grain structure. Now you can really see that rough versus fine. So you can see the fine and then the rough grain structure. The soft core is what allows this shaft to bend or rotate 360 degrees in return. And then the hardened steel shell is what brings it kind of back to shape. So that hardened steel shell makes the part work where it's supposed to work in terms of, the foot-pounds of torque, the weight ratings, everything that the commercial truck's seeing, 80,000 pounds, 15,000 foot-pounds of torque, everything is going to come through this hardened shell. So soft core, hardened shell tells me the part was heat treated. So I'm not going to think that there was something bad here that caused this part to break because I can see the grain structure. What I am going to look at is I'm going to go and I'm going to rotate around to the origin, nice and slow, and we can see something there. Heck, this camera is so amazing that you guys can actually see the issue in the shaft. How many of you guys have dropped an axle shaft on the floor or slammed it on the side of your bench and put a nick in it or put a dent in it? And if you have, that's going to be where that shaft breaks. Maybe you didn't know, but our shafts are not perfectly round. We shot peen them. So we take all the stress risers out of the surface of this shaft. And someone whether it's a tow truck driver, a technician, a parts guy, somebody nicked this shaft with either the edge of a bench, the edge of a toolbox, a cutting wheel, something put a massive dent in this shaft. That little nick in the shaft, that little dent, is what caused this shaft to break. Because we just stuck it back in the truck. We didn't think nothing of it. So that one little dent, that one little stress riser is all it took for this shaft to snap in this location. So I have my origin. I have my origin or my ratchet mark where it started. And then I have a small roll in the steel here where this was dented at some point in its life, which caused it to break here. So back to camera one. So this shaft twisted up, loaded up, and it did that a few times. And then eventually when it loaded, it snapped all the way around and finished itself off. So again, one small nick in the surface. Now, if we would have took that nick in that shaft and we would have maybe put a radius on it, there's a good chance that if we radiused it and took the high chunk, the raised steel out of it, that shaft probably could have survived. But we would have had to radius that out and make sure we had no 90-degree or sharp edges on that shaft to cause that break. So if we go back to camera and we look at example 2 here for the same type of failure mode, you're going to see that when I follow my chevrons, right, and I'm looking at my chevrons, everything is pointing back to this location here. So I have my ratchet marker, my origin. I can see my grain structure all coming back and pointing to that origin. But when I look at the origin from the outside, I don't really see anything. I don't see a nick or a dent like I did on the last example. So this one is going to be just a pure torsional tensile fracture, meaning this thing was spun up and for some odd reason, the wheel did not want to release that energy and eventually snapped the axle shaft. So again, but the grain structure points to a hardened part and a properly made part. All right, I'm going to stay there right now, and we're going to go to what we call the torsional tensile shear. Whenever I find it. There it is. All right, so the torsional tensile shear is a similar break, but you can see there's no 45 on this. This is a straight 90-degree break. This is a hit so hard, so quick that the shaft never had time to rotate up and spin into place. It just snapped it. Didn't have any time to load or properly twist that shaft up like a barber pole. And we can tell how bad this shaft was hit when we look at the spline section. That is not me and some fancy camera work. That is a shaft that was twisted beyond coming back. So we can see where the driver controlled diff lock collar was and how the diff lock was impacted hard against the spline section. and that this diff lock never worked again because the spline section was so twisted. So just one giant instant hit causing a 90-degree like pipe cutter, cutting wheel, whatever you want to call it, cut the end of the shaft right off. But if I look at this, I'm going to do my best. It's kind of, it ran for a while on the other half of it, but we can see out here I got a fine grain structure and a coarse grain structure. So I know I have a heat treat hardened shell, and you can see my ratchet mark right here. So this is where it started, and it looks like I got another one over here where it finished the break off. So I have two origins. This is probably my original right here where it originally hit. So again, if you put a nick in the shaft or a massive dent, try to radius it and smooth it out so you're not leaving a 90-degree or a stress riser in the component. Things happen. We drop stuff. All right. Where are we going now? Let's see. Keep going. Or skip that one because that one's rare. Keep going. All right. Yep. Perfect. Exactly where we need to be. All right. So now normally this presentation is 2 hours, right? I go to a little bit more detail of what each failure mode is. I'm giving you guys kind of the crash course of it. So the next thing we're going to look at is fatigue failures. So we've done lubrication failures. We've done instantaneous failures, right? So, and now we're going into fatigue failures. Now fatigue failures have so we've talked about shock load, spin out, gone over mountain peaks and chevrons and how those point back to our origin, point back to our starting location. Now we're going to get into a thing called fatigue. Now fatigue is going to be a cyclolytical failure, meaning this driver is cyclolytically overloading his components. Now, how is he doing that? There's 2 ways to do that. You have your torque, right? Engine's programmed wrong, which we know is kind of a rare one, or someone changed the programming and upped the torque on it. And then there is overload. So too much weight on the truck. And typically we see too much weight. More often than we're going to see.
I don't know.
More often than we're going to see misprogramming, right? So the main thing, you got it? All right. The main thing we're going to see with fatigue type failures.
They can hear you, Doc. They can hear you. Yeah.
Yeah, we're muting you guys. It's all right. You guys are good. It's fine. It happens every class. If you want to unmute to ask questions and talk, feel free. But so with the fatigue type failures, we're looking at some type of application issue. Are we using the truck for what it was bought for? Not what they think it was bought for, but what it was actually bought for. Like when you look on your build sheet from the OEM and it says Walmart line haul, and then a truck gets sold and it says Jim Bob's tree service chip hauler. Okay, those axles, brakes, drivetrain, that wasn't designed to be in a chip hauler, right? So how are we using the truck, and are we using it appropriately for what it does? So let's look at some fatigue failures up close and personal. So this is a pinion. Everyone familiar with that? This is actually going to be a forward drive axle pinion. So if you're not familiar of seeing pinions out of trucks, we really don't see them that often. But if you're looking at a pinion in the spline sections more towards the middle and not at the threaded end, you're looking at a forward rear pinion. And if the spline section's out at the end near the threads, you're looking at a rear pinion. It's that simple to dictate. So when we look at the pinion, it looks completely and utterly fine. Well, let's roll it over and take a look at its other side. Woo, look at that. That's a deep one, right? Check it out. There's your tooth, right? They call this root beam fatigue, and they call it root beam fatigue because of why? It looks like your dentist went in there and yanked the tooth out of the pinion, like so. So I'm going to try and zoom in and get these marks for you. They look pretty good right there. I like it. All right, so is everyone seeing these tree rings? All right. So these tree rings right here are called beach marks. The more we have, the more bending we have. Can you go to camera 1 just for a brief second? So what beach marks are are essentially is what I call the coat hanger. So all of us have taken a metal coat hanger and we've bent it in half, right? So when it comes to fatigue failures, we're looking at a balance between cycle versus load. Meaning, if I take a coat hanger and I bend it like this, how long is it going to take me to bend through it? An eternity. Versus if I go all 90 degrees and back to 90 degrees and 90 degrees again, that coat hanger is probably going to break in 3 bends. Versus like this, it's going to take a hundreds of amount of cycles to get the crack we need to form and to get the break we need to happen. So cycles versus load. So when we're looking at beach marks, the tighter they are together, the closer they are, right? So in this instance, let's say we're like that, right? We're close together. That means I have a lot of cycles. I'm overloading for sure, but I don't have a lot of cycles. I'm getting very close beach marks versus beach marks that look like this, where I have a large gap between them. That means I'm severely overloading and I'm not getting as many rotations or cycles through the system. So when we go back to the part and we look at this part, we can see a number of cycles through here. So this thing had overload, but it made it through a number of cycles. So the overload was there, but it was not as severe as you would think. So it's not an 80,000 pound overload. It's probably more like a 10 or 15,000 pound overload. And he did that many trips with it or tried it that many times. So each time they instituted a crack. So if we look at our chevrons, our mountain peaks here, right? They all point back to here, to here, to here, to here, to here. And if I look at my gear tooth here, right? So I have an origin, an origin, an origin. All my chevrons are pointing back to these origins. On a curved part, like we're seeing here, because this is curved, we're going to have a multiple cracks and multiple starts of those cracks. So you can see slightly right here through the middle, you can see those beach marks or those swirls or those ripples. I always compare beach marks to throwing a pebble in a lake and watching the ripples come off of that pebble. Small pebble gives you lots of ripples, low load. Big pebble or big boulder gives you small ripples or large ripples, but very little cycles of those ripples. So this is fatigue. This is overloading your truck, whether that's weight or torque. And if we rotate this part around and we look at other sections of it, we can see crack in the tooth. I got another crack right here. Every tooth on this pinion is most likely cracked or broken. And we got another crack here for this tooth not coming out. So I got another one there. And I think there's a crack somewhere right here. So again, fatigue. This took time. This took a lot of energy. The only thing you can say is let's look at your weight tick and see if you're using the truck properly. That's the only thing you can do with a root beam fatigue with that center position failure. We're going to look at other fatigue failures that may not be this centered or this pretty. That'll give us a different diagnosis. So again, some type of overload caused this failure mode. All right. So from root beam fatigue, then we go to what we call positional. So if we look at this pinion, I'm zooming out, there we go. If we look at this pinion, everything on this gear tooth looks basically good, except for the heels. All the heels are busted off. It's what we call a positional issue. So I do have, it's definitely fatigue life, right? I have my ripples and beach marks through that section right there. Get in there. So you can see the ripples and the beach marks. That leads into an instantaneous rough and crystalline fracture. Because eventually you bend through here and then there's nothing left of the gear tooth to hold. So it doesn't bend all the way through. It snaps off and finishes in a rough and crystalline finish as in an instantaneous overload. So what would I look at for this? Well, first things first is what type of mileage, you can go back to camera one, Pete. First thing I would want to look at is what type of mileage does this have? Is it high mileage or is it low mileage? If it's under I'm going to say under 50,000 miles, I would consider low mileage for any commercial truck. So if it's under 50,000, I'm going to think, huh, did Cummins Meritor build me a wrong carrier? Is the carrier built wrong? Meaning the relationship between the ring and pinion isn't quite right. And we call that a positional issue, meaning we're either going to load the heel of the gear or the toe of the gear, when what we're trying to load is that center third on a ring and pinion. Center third, top to bottom, center third, front to back of the tooth. So if I put the pinion in too far, meaning my pinion depth is wrong, I could load the heel of the gear. If I pull it out too far and set it back too far, I could load the toe of the gear or the front of that gear. So when we're looking at this example with all the heels broken off, I got a couple different options. Is he overloading the truck? Well, if he's under 50,000, I'm going to look at original build. I'm going to look at that first. Is the carrier set up properly? Now, if I'm over that 50,000 mile mark, and I say 50, probably going to be lower if it was built wrong. If I've gotten to 150, 200, 300,000 miles, and then I see this, I'm not thinking it was built wrong. There is nothing in our industry based on our torques and our loads that's going to last any significant amount of time if it's built wrong, right? When you're seeing 15,000 foot-pounds of torque in first gear and you built it wrong, it's not going to last very long. So we usually don't see wrong builds happen at high mileage. So if I have that higher mileage, that 200, 300,000 mile mark, I'm going to be thinking, well, do I have a lubrication issue going on? Is my pinion now moving? Do I have a bearing end play issue that's caused due to bad or wrong or depleted lubricant? Was there recent maintenance done? Do I have a seal leak that is allowing moisture or water to get in the axle, which can cause end play to grow and my pinion to move? So I'm going to be taking pinion end play, making sure I still have that zero pinion end play. I'm going to look at yoke nut torque or breakaway torque on that pinion to determine if someone did do a seal, they torque the yoke nut properly and set that preload back into standard. So, or set it back to spec. So remember, pinions and ring gears are the two things in our portfolio that start out with a below zero end play. So my rule of thumb for end play growth, which is not written in any book, it's not written by engineering down here, 50 feet to our right. It's literally from my experience of being on the phones, talking to you guys as technicians. And my rule of thumb is that you're going to get 0.001, so 1/1000th of end play growth per 100,000 miles. Is that concrete? No, but it's a great way to gauge whether your truck's wearing properly or excessively wearing. Because if you got 100,000 miles and you have 5/1000ths of pinion end play, which is supposed to be zero, you know something is significantly going wrong. So check your lube, check your torques, check to make sure everything's built properly. So that's why end play is going to grow over time. We can't stop it from growing, but we can monitor it and make sure it's growing respectively as the truck ages. Now, I do not, same thing now, if you have a dump truck, I would expect way more end play growth in a dump truck. What's a dump truck do that a line haul doesn't? As much starts and stops, right? If you were to compare pinion end play of a garbage truck with the same mileage as a Walmart truck, that Walmart truck's going to have a much tighter carrier set and a much more put together carrier set than that garbage truck is. Those starts and stops are what determine that pinion and main diff bearing life. So that's why line hauls get 750,000 miles of warranty and garbage trucks get a 2-year unlimited mile warranty, because those starts and stops abuse the bearing set on these heavily. So remember, the more time you spend in first and second gear, the higher torque numbers you're putting down, the more bearing wear you're going to cause. So, all right, that was positional issues. All right, what's our next one? We had next one, spalling. Spalling's a hard one for me to film. All right. Spalling. I'm sure you guys spalling on a bearing. Mainly because it's really the only example I got. So when we look at this, what is spalling? Spalling is a pitting of the surface. It's actually fatigue. Why is it fatigue? Well, in order to get spalling that we're seeing here on cam, you have to get rid of the oil. Now, does that mean it didn't have any? No. What did we say is a good sign of no oil? Burnt. This is not burnt. This looks pretty good. It's got a little rust on the cage, but it's been sitting in the training room for a while now. So, but if I look at these rollers, they're kind of spalled at the small end of the bearing. Now, what is spalling? Is there, Pete, can you go one more slide? Is there any way to show them that? Yeah. We're going to pull up one slide for you. We didn't really want to do PowerPoint with you guys today, but there's a slide that kind of will help a lot of you. There you go. So you can go cam 1, 2. So when we're looking at the slide, this is Timken's. This is not us. We use basically exclusively we use Timken bearings. So when we look at end play growth from the 0 line, you can see that we're not using the whole roller. We're using like 3 fingers of the rollers, right? We're using half of the bearing at a 0 end play. Below 0, we start to load and use a majority of the bearing. So we actually put a slight or light preload on our pinion and main diff bearings, which gives us to that right of that dotted line there, which means we're using much more of the bearing to spread the load. Now, when we get to the right side of the dotted line, you're going to be looking at wheel ends, input shafts, output shafts, right? Everything that has an end play spec to it with a tapered roller bearing, we're looking to the right. So when you see a hub with 10 thousandths of end play, well, that's exactly why the bearings got pits in it, because what happened was as the end play grew, we took the load from the 3 rollers and we put it to 1. And as we put it to 1 roller, cam 2, and as we put it to 1 roller, we end up spalling those rollers because there's so much pressure and weight on that roller. We've squeezed all the oil out. Even though this is submerged in oil, there is so much pressure and weight and load on this bearing that the oil can't get to where it needs to, which is between the cup and cone here. So that's why we'll see end plays grow substantially in terms of once we start that wear characteristics. All right, so I know I see it. So that is spalling. There's only really one last thing to talk to you guys about since we didn't talk about it, and that's going to be lack of heat treat. So that's our last example for today. So if I look at this gear, we can see that this gear, all the way out, okay. We can see that this gear has excessive wear. We can see the depth of the wear into the teeth. There you go. You can kind of see that depth of wear. So this is a lower helical gear of a forward rear axle. It was put up against a hardened gear. So let me flip. So now we can see the spalling. And again, it was just because that the gear was soft, everything kind of mushed together. So it is a surface fatigue, the spalling. It has nothing to do with end play growth in this instance, but it is a surface fatigue. The surface wasn't hard enough to take the load, so the surface started popping chunks of metal out, and that gives us our spalling. When we look at the gear and how it failed, we can see that the teeth kind of just rolled over themselves, and they didn't break off. And then another giveaway, which you guys can see on cam, which is good, is these teeth that are flailed out. So when we harden a gear, the edges or heels and toes of that gear are very brittle, because you can't carry your soft core out to the edge because heat treat is going to wrap around this. So that's going to make the edges of any gear very brittle, which is why we don't recommend rolling the carrier across the shop on the ring gear. That's how you break all the heels off. And yes, that has happened. And yes, I have seen it. So massive difference between lack of heat treat, as you guys are seeing here, lack of heat treat, splayed ends, teeth rolled over, versus cam 1, versus shock load, where we have the rough and crystalline break. There's a massive difference between the two. So I know that probably felt rushed because it felt rushed on my end. So I hope you guys had a good time. I hope you learned a little bit of something. Again, if you need any help in analyzing your brakes or analyzing what happened to that truck, feel free to send pictures into our call center. They will gladly help you figure out how that broke and what happened to it. You may not agree with it, but we do have a parts failure analysis book. It's free. It's on our website. It's TP0445. It has all of these examples in it, and it explains in depth how those examples come to be, how they come to pass, and what causes that to happen. So our call center guys are trained extensively in failure analysis. I'm their trainer. So if they get one wrong, we're all human. We get them wrong, right? We're all learning every day. So don't hold it against them if they get one wrong. If you want it reviewed by a more seasoned person or someone level up, you can ask for that level up review. So we're always here to help. We're always here to guide you guys on anything you need. So I hope it was informative. I thank you for coming, and I hope you have a great rest of your week.
Awesome. Thank you very much, Jason. I appreciate that. So just so everybody knows, I will be following up with an email that will have a link to a video recap. Well, this video actually of the training that you just sat through, because there was definitely a lot that was covered. And then that information that Jason just shared with you, the call center phone number and the reference guide, I'll look for that information to include as well. That's all we've got for today. Again, we really appreciate you all jumping on the call with us, and we look forward to seeing you at future Kenworth Northeast Training Academy sessions.